In this lesson, we examine contour maps, or level curves, of multivariable functions. Essentially, contour maps provide a two-dimensional representation of a three-dimensional object. These maps are commonly used to display topographical data or weather-related measurements. This is an example of a contour map for the temperature across the United States. This is an example of a topographical or elevation map. To create these maps, we form a series of level curves. Level curves are formed by finding all input values for which the function's output is a fixed value, say c. Geometrically, the level curves result from the intersection of a function f of x comma y and a plane z equals c, parallel to the xy plane. We now take this collection of x comma y points and graph them on the xy plane. This two-dimensional plot is called a level curve or contour line. A collection of level curves is called a contour map. Curves corresponding to different levels, or z-values, can be distinguished by color. Other times, a simple label is used to denote different contours. Let us now take a look at a simple function whose graph has a hill on one side of the yz plane and a valley or crater on the other side. Looking at only the two-dimensional contour plot without color or markings, it is difficult to determine which side is the hill and which is the crater. This is why it is imperative to provide some means of distinguishing the different levels involved in a contour plot. Otherwise, a significant amount of information is lost when moving from the three-dimensional surface plot to the two-dimensional contour plot. We end this lesson by noting that the techniques described here can be applied to surfaces where one coordinate is not a function of the others in a similar manner. When you are dealing with surfaces that are not the plot of a multivariable function, there is a chance that the contours will intersect or even overlap. Consider the example of the hyperboloid of one sheet. This surface cannot be described by a single multivariable function where one coordinate is a function of the others. Due to the symmetry of the hyperboloid above and below the xy plane, the level curve at z equals c is the same as the level curve at z equals negative c. The contour map on the right is difficult to read. Carefully picking levels can avoid this situation entirely and requires a strong understanding of the surface to begin with. Take a look at the new contour map where the levels were more carefully chosen. This time there is no overlap. This concludes the lesson on contours of multivariable functions. You should use the contour plot demo for further exploration. You can look down to go to the main menu and select another lesson or demonstration.